bridge works again? Didn't quite understand.
When, say, this is going, the zinc 2 plus ions are turning into zinc metal. Is that right? No, other way around. Zinc's going to zinc 2 plus ions. And so when you start off, that beaker has got a solution, say, of zinc sulfate. And so if you, say, had a litre of it, you'd have 1 mole of zinc ions and 1 mole of sulfate ions. When the reaction starts, you start making more zinc ions. And if you don't do anything other than that, then you're going to end up with more cations, more zinc ions, than you have sulfate ions in that solution. And you can't have that, because then you'd have a charged solution. Right? And the cell will stop working, because it can't make that. And so what the salt bridge does is it adds more anions to balance up these extra cations that are being made by the redox reaction. So you've just got this wet filter paper with potassium chloride sitting in the solution. And before you start, those ions are going to stay in the filter paper. But when this reaction starts and you start making zinc ions, chloride ions from that wet filter paper are going to start leaking out into the solution as well to make sure that you've got the same number of cations and anions in the solution. Does that make sense? Yeah? Okay. Right. So now on to what the number tells you. So the voltmeter will have a number on it. And the number we can relate back to our tug of war. In the tug of war, we saw that we had different numbers of Jonolomus pulling on the rope, and the team with the most Jonolomus won, because it had one more Jonolomu than the other side. Right? In our galvanic cell, both sides are trying to gain electrons from the other side and get reduced. Right? Zinc 2 plus wants to get electrons and turn into zinc. Copper 2 plus ions want to get electrons and turn into copper. So in theory, both of those sides are pulling electrons off the other side. But one of them will want them more, and what we've seen by the sign of our voltmeter is that it's the copper side that wants them more, because the electrons end up going from the left-hand side across to the right-hand side. So it's not that the zinc doesn't want the electrons. It just doesn't want them as much as the copper does. Yeah? The reading on the voltmeter, the number on the voltmeter, gives us a number to quantify how much more the copper side wants the electrons than the zinc side does. And so this is given the symbol, the reading on the voltmeter is given the symbol E standard cell, and I'm just going to put in there the name that we give that, and of course that's going to be, yes, toolbox, and off, close. The standard, now it's not even typing, yeah, ooh. Right. And we read, when we say E standard cell, what that means is a standard cell potential. Not a reduction potential now, but the cell potential under standard conditions. And we have a formula. And the formula goes like this. And everybody's probably seen this formula. Well, at least if you've done any sort of this stuff at school, because this is the standard thing they always ask you about. We can say that the value of the standard cell potential, E standard cell, is just the difference in the reduction potentials of the two sides. Right? So it's the reduction potential of the right-hand side of your galvanic cell minus the reduction potential of the left-hand side of your galvanic cell. Now note, please, 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 that this is the reduction potential of the right-hand side minus the reduction potential of the left-hand side. One of those sides will not actually be doing a reduction, but it doesn't matter. We put in the reduction potential numbers because there is no such thing as an oxidation potential, right? The E standard cell is telling you about the difference between how much each side of the galvanic cell wants to get the electrons for itself. So both sides are pulling. The E standard cell tells you about who wins, who's pulling more, and by how much. Right? So please don't, and if you've been taught this, then I'm not going to dwell, but don't go changing one of the signs of these because you go, oh, but the zinc's being oxidized, so I have to change the sign on this number because it's not a reduction, it's an oxidation. Don't do that. The little equation's smart enough to deal with that. Right? So you always put in reduction potentials. Yeah? In this case, it's going to be E standard for copper 2 plus copper minus E standard for zinc 2 plus zinc. Because the way we've drawn our galvanic cell on our page is that the copper 2 plus and copper is on the right-hand side and the zinc 2 plus and zinc is on the left-hand side. Note that we don't care about whether this is going to give a positive value for E standard cell or not. It doesn't matter. And if we were to build such a galvanic cell, and we were to look at the voltmeter, then the voltmeter would read plus 1.10 volts. Okay? So this is the standard cell potential for that galvanic cell. And so what it's telling you is that the difference in the reduction potentials between the copper redox couple and the zinc redox couple is 1.1 volts. The copper side wants the electrons more than the zinc side by 1.1 volts. Now obviously that doesn't necessarily mean anything by itself, but this is how we start to get these numbers and start putting numbers on stuff. Right? Okay. The fact that the value for E standard cell is positive confirms that the right-hand electrode, in this case the copper, is the positive electrode. Right? That statement's a little bit redundant given what we've already said. So it's the one where the reduction is occurring. We say that the polarity of the right-hand electrode is positive. And the value of E standard cell tells us how much more the copper 2 plus copper side of our galvanic cell wants the electrons than the zinc 2 plus zinc side does. So the voltmeter gives us a value for the standard cell potential. It tells you the difference between the pulling power of each side of your galvanic cell. It tells you how much more one side wants the electrons than the other. What it doesn't do is tell you what the actual reduction potential values are. Right? It only tells you the difference between them. If we go back to our Jonah Lomu tug-of-war thing, the right-hand team won because they had 3 Jonah Lomus, whereas the other side had 2. But if we were to think about that in terms of our voltmeter, the voltmeter would only tell you that there was one more Jonah Lomu on one side than the other. That could mean that there's 3 on one side and 2 on the other, but it could equally mean that there were 5 on one side and 4 on the other, or 12 on one side and 11 on the other. The difference between them is still only 1. And this is the same thing here. The value on the voltmeter will only tell you about the difference between the reduction potentials, not what the reduction potentials actually are themselves. And so if we want to work out what the actual individual reduction potentials are, then we have to do something slightly different. Obviously we can't measure them in isolation because you can't have a reduction occurring without an oxidation somewhere else. Right? You can't build a galvanic cell with only one side on it. Nothing's going to happen. And so what we do is this. The only way in which we can determine the value for E standard of copper 2 plus copper, so if we want to work out the reduction potential of the copper 2 plus copper redox couple, then we can only work out what that is if we build a galvanic cell and we know what the reduction potential of the other side is already. Right? If we know what one side is, and then we can measure the difference between the two sides with our voltmeter, then we can work out what the copper 2 plus copper 1 must be. But we have to know what the other one is. Right? And then we kind of get into a chicken and egg thing, and you know, at some point you have to know one of them in order to work out the others. And so the way that you get around that is that you say, okay, I'm going to take one of these redox couples and I'm going to call it a number by definition. And so some old man with a beard 100 years ago said, let's do this. Let's call a particular one, let's say that a particular redox couple has a reduction potential of 0. Right? It doesn't mean that the thing doesn't want to get electrons. It means someone just woke up one morning and said, let's call this one 0. Because if we do that, then if we start building galvanic cells with that redox couple in there, then we can start putting numbers on everything else. Because we've defined this one to be a particular number. Yeah? And so the one that was defined to be 0 is this H plus H2 redox couple that we saw before with the hydrochloric acid. Right? So someone just invented that. It could have been any other redox couple you like, but for some reason that I don't know, they chose this one. And so what we can do then is we can build a little galvanic cell that looks like this. On the right-hand side, we have our copper, like we had before. So we have a solution of copper 2 plus ions with a concentration of 1 mole per litre, and we have a piece of copper metal sticking into it. And on the left-hand side, we have our redox couple for the H plus and the H2. And so this is a bit complicated because it's got a gas in it, right? So what we have is we have a solution which contains H plus ions at a concentration of 1 mole per litre, right? So this is just acid with a pH of, anyone off the top of their heads? The concentration is 1 mole per litre, then the pH is negative log of 1, 10, 0. So the pH in here will be 0. So this is quite concentrated acid, yeah? And then we have bubbling into this some H2 gas. And the pressure of that gas has to be 1 atmosphere, so you have to set things up so that pressure's right, so it's standard pressure, right? And it's bubbling through here, and as it bubbles through, then in theory the H2 gas can turn into H+, or the H+ can turn into more H2 gas, depending on which way the reaction actually goes. The thing with this redox couple, as opposed to the copper one, is that if you've got H2 and H+, then neither of those are something you can attach your wire to. Right? There's no piece of metal on this one. And so what you have to do is you have to have some sort of electrode, because you have to attach the wire to it somehow to get to the voltmeter on the other side. And so what we do is we use a piece of metal that's not likely to react in the redox reaction at all. And so that tends to be something like a piece of platinum, right? Something that's very unreactive. So when you hear unreactive metal, you think expensive metal. So platinum or gold or something like that, right? So typically you use a piece of platinum, So here's a platinum electrode here. That's just there to get the electrons in or out of the solution. It doesn't take part in the reaction itself. And then we have a salt bridge like normal, and we have a voltmeter and a wire like normal. Right? If we do this, and we look at our voltmeter reading, then we find that the right-hand electrode is positive, because the reading on the voltmeter is positive. And so that means that the electrons are going from the left-hand side to the right-hand side. And so that means that the oxidation reaction must be H2 gas being oxidized to H plus ions. And the reduction, the reaction which happens at the positive electrode, will be the copper 2 plus gaining electrons and turning into copper metal. Okay, so the voltmeter reads a positive number, and so we can get all this information just from that. Here's the cell diagram that you would write for this. The right-hand side of the cell diagram is just what we saw before. The left-hand side's a little bit different, because now we've got the platinum in there as well. Remember, the things that you write on the farthest outside parts of your cell diagram are the things that the wires are attached to. So in this case, that'll be the platinum, right? So platinum, and then a line, and then the H2 gas at P standard pressure, and then a line, and then the H plus ions dissolved in the water at standard concentration. And that thing on the left-hand side has got a wee name. It's called the standard hydrogen electrode, and that's oftentimes abbreviated as SHE. And so now if we come to the number on the voltmeter, which tells us about the difference in the reduction potentials of the two sides, then what we can do is we can write out our little formula. E standard cell equals E standard of the right-hand side minus E standard of the left-hand side. Put in for this particular thing, it's going to be E standard for the copper 2 plus copper redox couple minus E standard for the H plus H2 redox couple. The reading on the voltmeter is going to be plus 0.34 volts. That's what you would read if you built that galvanic cell. So you write that in on the left-hand side. And then that's going to equal E standard for the copper 2 plus copper redox couple, which we don't know, minus 0. Because we defined the reduction potential for the H plus H2 redox couple to be 0. And so then hopefully you can see that the E standard for copper 2 plus copper must be plus 0.34 volts. And so this is how we would go about working out what these individual reduction potentials are. Right? So the number, if you like, isn't an absolute number, it's a relative number. The 0.34 volts tells us that this redox couple wants to get electrons 0.34 volts more than H plus H2 does. Right? So all these numbers are relative, but it doesn't really matter because it's still going to give us the information that we want, which is to know which thing is going to be oxidized and which thing is going to be reduced in a particular redox reaction. Yeah?
Why does it actually want it more? What is it in this?
Why does it want it more? Why does it actually, in a deep philosophical, theological sort of a way, want it more? If I said not for any reasons that we have taught you yet, that's probably the safest thing. So it's nothing to do with charge. It's nothing to do with how many positive charges are on it. It's not, well, it might be to do with electronegativity, but not in an obvious way either. It's just an inherent thing. I was about to say something very naughty about teenage boys, but I won't then. If you wanted to do it for the zinc, then you could do the same thing, right? You could build another galvanic cell now where you had your zinc 2 plus and zinc couple on the right-hand side and the H plus, your standard hydrogen electrode, on the left-hand side. You always put the standard hydrogen electrode on the left. That just keeps the math a bit easier at the end. Yeah? You don't have to, but it keeps it a little bit easier at the end. So if we were to build this, maybe don't draw that, but just draw that when we get to it, because that's kind of the point of a cell diagram, is to summarize the picture. If you build that, what you find now is that the reading on the voltmeter is negative. So that means that the right-hand electrode is the negative one. So that's where the oxidation is happening in this case. So the zinc is being oxidized to zinc 2+, and the electrons that are being released by that reaction are going across to the left-hand side, reacting with the H+ ions to make H2 gas. So the electrons go the other way in this time. Right? So the left-hand side is where the reduction occurs. The right-hand side is where the oxidation occurs. Here's the cell diagram for that. And so what we can do then is if we read what our voltmeter says and plug it into our little formula, the reading on the voltmeter is negative 0.76 volts. Negative, and this is why we say that the right-hand electrode is negative, but negative 0.76. And so the same sort of math applies. We can say negative 0.76 volts equals the reduction potential for the zinc 2+ zinc couple minus 0. Hello?
So the standard hydrogen electrode, is that the one that you always make 0 volts?
Yes, by definition that is 0 volts. Always. Yeah. And so it follows then that the reduction potential for the zinc 2+ zinc is negative 0.76 volts. Right? So what does that tell you? That tells you that H+ wants to get electrons and turn into H2 more than zinc 2+ wants to get electrons and turn into zinc. So the number for the zinc couple is negative. All that's telling you is that it doesn't want the electrons as much as the H+ H2 redox couple does. Right? It isn't saying anything deep and meaningful about which way electrons go and that it really actually wants to give them away rather than get them or anything. It's a relative number to how much the H+ wants to get electrons and turn into H2. Yeah? We happy? Getting there. Almost there. Now that we've independently found those two numbers, it should be that we can combine those together in our original galvanic cell and be able to calculate the value of the standard cell potential. Yeah? So this is what we had before, but now because we've gone and built these other galvanic cells incorporating our standard hydrogen electrode, and we've independently worked out the values of the reduction potentials, then that means that we should be able to predict what the standard cell potential for this galvanic cell is. If we put in the numbers, it's going to be plus 0.34 volts for the copper 2+ copper, minus negative 0.76 volts for the zinc, and that comes out as being plus 1.10 volts, which is what we saw before. What this is pointing out is that, so this is the same galvanic cell now, but everything's swapped around, right? So the copper's now on the left and the zinc's on the right. And the question is, what difference, if any, does that make? Now, should it make any difference to what the redox reaction is? No. Right, we're happy with that? If we build the galvanic cell and we draw down a picture with it like this, then we walk around the other side of the table and we draw a picture with it the other way around, it won't affect the reaction that's happening. What it means is that when you go around when you swap it around the other way, the numbers just go like this, right? It's E standard for zinc 2+ zinc minus E standard for copper 2+ copper, and so it's negative 0.76 minus 0.34, so the value is negative 1.10. But all that's really telling you now is that instead of the right-hand electrode being the positive one, the left-hand electrode is the positive one, which is exactly what you would expect if you walked around the other side of the table and looked at it from the other side. Yeah? So this is something that we get very excited about at school, how the E standard cell has to be positive. Well, it doesn't. You just got to know what a negative number means, right? It just means that the oxidation reduction are happening on the other sides. And I'll see there's lots. Oh, God, you don't want to do that. Maybe write that down. And we'll call that, and we'll leave it at that. So in general, for a galvanic cell, what we can say is that if E standard cell is positive, then the reaction in which reduction occurs at the right-hand electrode, is spontaneous. Okay, we'll leave that. And that can be a wee teaser for what that word really means for when we come back to it in first semester. Right? So if E standard cell is positive, then the reaction in which the reduction occurs at the right-hand electrode is spontaneous. If E standard cell is negative, then the reaction in which oxidation occurs at the right-hand electrode is spontaneous.